continue with chapter 5, which is a chapter on curves in R2 and R3. And in the previous video, we talked about what a circle looks like. So we're going to continue with that and then look at an ellipse in this video. Okay, so we continue with remark 5.1.9. So consider the function r of t, which is the vector function c cos t, c sin t, where t is from 0 to 2 pi. Right, so in example 5.1.8, we showed that this is a circle. So the range is a circle with center, the origin, and radius c. So the c here tells us the radius of the circle, and this circle is equation x squared plus y squared is equal to c squared, right? So we are going to note some points that we get from our vector function, right? So as t increases from 0 to 2 pi, the point r of t moves around the circle in the anti-clockwise direction. So as t is increasing, we know that, as the arrows show, we know that that's how the point moves around the circle. So it moves in the anti-clockwise direction, and it starts here and then it comes and ends there, which is at r of 0 and r of 2 pi, which is the point c0, right? And the sketch shows us that, right? So if we restrict the domain, we then get different parts of the circle, right? So for example, if we take RT, where t is from 0 to pi over 2, we know that we are just talking of the first quadrant of the circle with center, origin, and radius c, right? And if we have got a point p, which is p1, p2, which is a fixed point in R2, then the range s of the function, so suppose we've got a point p1, p2, such that we've got a vector function u of t, which is equal to r of t plus p, which we can then write in that way. Then this is just the circle with center p. So the center is no longer on the origin, it is now on p, and the radius will be the same. The radius will see it there, and so the range is just can be expressed in this way: x minus p1 squared, y minus p2 squared is equal to c squared, and the center will be obviously p1, p2, right? And this is exercise 5.1, number 3, that you are going to look at, right? Let's go on to another example, right? So here, when we talked of this one, we were in R2. So we want to see some example in R3 and how that will affect where the circle is situated. So consider the function r of t and this is a vector function in R. So this is a three-dimensional vector function, and it's 2 cos t, 2 sin t, and 3, where t is from 0 to 2 pi, and its range c, which is r of t, where t is between 0 and 2 pi. So what we want to show is that c is the center in the plane with z is equal to 3. So C is the circle, so it's supposed to be circle in the plane z is equal to 3 with its center at 0, 0, 3 and the radius is 2. So the radius, we can see from there that the radius has to be 2, and this tells us that it's not on the origin, but it's on z, on the plane z is equal to 3. We'll see that in a moment. So let S be the center in the xy plane with center 0, right? So if we consider, if we ignore the z plane, so therefore we can think of, we can create a new function u of t, which is 2 cos t 2 sine t 0. That tells us that the circle that we are talking about is in the xy plane. So we know that if this is the case, then it is range S, where S is just the circle that we already know, right? And that's what we did in example 5.1.8. So let's now think of a point in R3, which is on C. So we created a new one, S. This is the circle. My apologies again. S is the, let S be the circle in the xy plane with center 0. So it's represented by that. So now we need to think about a point that is on C, and in this, and C is our range of the object in R3, right? So a point X in R3 is on C if and only if X is equal to R of t, which is 2 cos t plus 2 sine 2 cos t 2 sine t 3, and we can then decompose that into that and that, and that's just equal to u of t plus 0, 0, 3, right, for some t in between 0 and 2 pi. So therefore X is in C if and only if X is written, can be written as X is equal to Y plus 0, 0, 3 for some Y in S, right? And then hence X, Y, Z is in C if and only if X, Y is in S and Z is equal to 3. Right, and what does that mean? That means that X is equal to X is in C if and only if X squared plus Y squared is equal to 4. So that is giving us our circle, and then Z is always equal to 3, right? So hence C is the center in is the circle in the plane with equation Z is equal to 3 with center 0, 0, 3 and radius 2, right? Because we are told, so if we think of this, we know that that is just a circle, but we are told Z is always equal to 3. So it means that we have to move the circle from here up until to the plane Z is equal to 3, where the circle resides, right? So that's why the circle is there. It's because Z is always equal to 3. So that means, and you know that this is an equation of a plane, so that tells us that the circle is moved upwards 3 units, right? Let's look at another different type of object, and we find this one in example 5.1.1. So consider the function r of t, which is equal to a cos t b sine t, where t is from 0 to 2 pi, and where a and b are constant real numbers. So in the previous objects that we were looking at, the the constants here were the same, we would have c cos t, c sin t. But in this case, there is an allowance for a and b to be different, for the constants here to be different, right? So what we want to show is that a point in the range of this uh, is has to satisfy this equation: x squared over a squared plus y squared over b squared, which is equal to 1, and we will talk about what that object is called. Right, so and then yes, when we sketch the curve, we'll then know what it is called. So um, so consider a point x in C. Then x is equal to r of t for some t um, between 0 and 2 pi. So if we then substitute, so what we want to show is that this is an if and only if statement, is a characterization. So if we start with a point in there, we want to show that this is equal to 1, right? So if we start off with x squared over a squared plus y squared over b squared, and then we plug in the x that we are given, which is a cos t, we get a squared cos squared t over the a squared there, and then plus, and then we substitute the y here, and then we get that, and this is just cos squared t plus sine squared t, which is equal to 1. So therefore, if x is in C, x is in the range of R, then it satisfies this equation, right? Now we want to talk about the converse, right? So let x be a point in R2 that satisfies this equation. We want to show that that point is going to um, be in C, and therefore we get our if and only if statement, right? So let uv be equal to x over a and y y over b. Then u squared plus v squared is equal to x over a squared plus y over b squared, and that is equal to 1, right? Now, so what we are trying to use here is what we know already. We know that u squared plus v squared is equal to 1 becomes something like a circle, right? That's what we did in example 5.1.8. So so according to example 5.1.8, there exists a real number t, so that u v is equal to cos t sine t. So if this happens, we can see that this is, so u squared plus v squared is equal to 1, indicates that we've got a circle with center 0, center the origin, and radius 1, right? So we know that we can, if this happens, by the if and only if statement that we did in example 5.1.8, it means uv should also be cos t sine t. This will be 1 cos t, 1 sine t, where the 1 is the radius, right? You remember, maybe let's just go back and see what we are talking about. So if you remember in example 5.1.8, we talked about something like that, and we showed that this a point is in C, is on C if and only if it satisfies that equation. So if we have got an equation like this, we know that we can express x and y in terms of something like that, right? So that's what we are doing in this example, right? So because we found this to be true, we know that uv can be written as 1 cos t, 1 sine t, where 1 is the radius, right? So, but what does that tell us? We assumed here that x over a, u is equal to x over a, and y is equal to, sorry, v is equal to y over b. So that tells us that x over a is equal to u, which is equal to cos t, and therefore x becomes a cos t, right? By just multiplying by a here, we get that. And then again, y over b is equal to v, which is equal to y, uh, uh, which means that y is equal to b sine t, right? So therefore, xy is equal to a cos t b sine t, which is r of t, and therefore x is in C. So the if and only if statement that we used, we got it from 5.1.8 to move from here to there. And this tells us that because we assume that u is equal to x over a, y over b, this tells us that x can be written as that which is r of t, which means that x is in C. So we now sketch the curve. So we've shown the first part, the if and only if statement in the question, in the example here. So now we want to finish off by sketching the curve, right? Where am I now? Okay, so we have said that this happens, right? X squared over a squared plus y squared over b squared is equal to 1. And we know that this can only be true. So if we find our y's, we see that we get two cases. Y will be the positive of, so if we take x squared over a squared on the other side, we multiply by b squared throughout, and then we are left with the square root of that, and then we can easily do this, right? So so we find that y is either the positive root, the positive of that, because remember we are taking the square root of y, so either the positive or the negative, right? Right. So we are going to look at both cases. So we consider that that part C1 of the curve given by, so we are taking the part where y is the positive, right? So for x between minus a and a, we have, so if we differentiate this function and equate it to 0, this only happens when x is equal to 0, right? And the second derivative, we can find it, and we find out that it's always less than 0, right? So C1 has a turning point at x is equal to 0 and is concave down. So this one tells us that the second derivative tells us that C1 is concave down on the interval minus a to a. And then we also have that the limit as x tends to a negative of dy over dx goes to minus infinity. And if we do the same, we also get that it for minus a positive is going to be infinity. Now, since y is which is equal to that defines a continuous function on the interval, we see that C1 has vertical tangents at x is equal to minus a and y and x is equal to a, right? So this is coming from these, that that's why the limit is going to minus infinity in that case and infinity in this case. It tells us that if we think of the tangents, they have to be vertical ones. That's why the values become infinity and minus infinity. And then so the graph that we have is that, and this is where the vertical tangents are, right? Right, now we consider the second part. So we were told that so just to add a bit, uh, we were told that we found out that the turning point is at x is equal to 0. So that is the turning point there. We have a dome shaped like that, and the turning point is here where x is equal to 0, right? Okay, so now we consider C2, the part of the curve where y is negative, right? And we will notice that that is just a reflection in the x-axis. We will do the same thing. So it's just a reflection of C1 in the x-axis, and that is xy minus C1 if and is xy is in C1 if and only if x is equal to x minus y is in C2. So therefore we have the following. So depending on which number is bigger, a or b, so in the here we had sort of assumed that a is greater than b, right, in this sketch. So if we look at the reflection, we get this now, right? When a is greater than b, when a is less than b, that means that the egg shape looks vertical like that, right? So those are the two cases that we get depending on uh, a being greater than b or a being less than b. And if a is equal to b, then we have got a circle, because they have to then be the same distance from there to there and from there to there, right? So we are going to talk about this curve in general now. So consider the vector function r of t. We are going to look at some things that we can take out from this example. So if you consider the function that we've just considered, r of t, where a and b are constants. So in example 5.1.11, it is shown that the range C is the curve with the equation that, and this curve is known as an ellipse, right? So we are going to note some points that we know about an ellipse. So you can think of an ellipse as circles which have been stretched out along the x-axis or the y-axis, right? Indeed, the ellipse fits exactly the circles with center 0 and radii I and b, respectively. See the sketch below. So this one has been stretched. So it's like this circle has been stretched, right, along the x-axis to get the blue one. And as this one says, it is between it. So the circle where the radius is b fits there, and then the circle where the radius is a fits there, right? So it's in between those circles. And as t increases from 0 to 2 pi, the point r of t moves along the ellipse in the anti-clockwise direction, just like the circle, right? But yeah, along the path of the ellipse, and also starts from 0 here and then goes up to 2 pi, which is the same point a0, and the sketch tells us that. Now the other thing is the ellipse is symmetric about the x-axis and the y-axis. So if you look at it, we can see that xy is in C if and only if x minus y is in C. So if we look at, we can always see the reflection there, and then the reflection in the y-axis, the points, we can see that from there, right? and then the ellipse with the ellipse C with equation x squared over a squared plus y squared over b squared is equal to 1 can be described in the following way. So assume that a is greater than b and let c be equal to the square root of a squared minus b squared. Then it can be shown that C, which is the set of all points, C, which is the set of all points in R2 such that uh, the norm of x minus C0 plus the norm of x minus C of 0 is equal to 2a. So we want to show that well, it can be shown, we're not going to prove it, but it can be shown that the distance, so we are talking of L1 and L2. So what we are saying is um, that has to be equal to 2a for the, so we can describe C in that way, that if we look at those distances we should be able to get 2a, right? So if we look at L1 plus L2, that should be equal to 2a, right? Okay, um, let's look at all the other points. So the points C0 and minus C0 are called the foci of the ellipse C, and we call the points A0 minus A0 the vertices uh, are we call them the points on C that are furthest apart. Um, right, so the x-axis is the major axis of C. You see the one with the furthest, with the points that are furthest apart. So because here we assumed a is greater than 0, so therefore this is going to be the one with the points that are furthest apart, right? And then we then call the x-axis in that case the major axis. Now if p is greater than 0, then we reverse here. We are supposed to say c is equal to b squared minus a squared, not a here, so it's supposed to be a squared. And then in this case the foci of C are at 0c. So here it was C0 and 0 minus C, sorry, C0 and minus C0. So we reverse that and we get 0c and 0 minus c, while the vertices are 0b and 0 minus b. And in this case the y-axis will be the major axis, right? Okay. And okay, and then I think this one is the last point. If P1, P2 is a fixed point in R2, then the range E of the vector function U of t, which is equal to R of t plus P. So now the center has been shifted, right? So excuse me, E will look like x minus p1 squared over a squared plus x minus p2 squared over b squared is equal to 1. So basically, if we have a fixed point and we have u of t to be r of t plus p, then we have shifted the center of this ellipse. And so if a, well, it's not the center, it's the foci, right? So if a is greater than b, then the foci of E are, so we have P1 plus C P2, P1 minus C P2, while the vertices of E are P1 minus A P2, P1 plus A P2. Right, and the ellipse is symmetric about the lines x is equal to P1 and y is equal to P2 respectively, and we can see the figure below. So we can see that it has been shifted, and this becomes our okay. So that so it has been shifted, and we can see all the information that we have been explaining here, right? The foci is P1 plus C P2 and P1 minus C P2. So P1 plus C P2 is that one, P1 minus C P2 is that one, and then the vertices are those ones, I think, right? P1 minus P2, P1 minus, sorry, P1 minus A P2 and P1 plus A P2, right? Okay, these ones, right? So therefore, that is what we have. Thank you. We'll continue with this in the next video.